Okay, so welcome back from the from the coffee break. We will continue the presentations of this morning with our external speaker, that is Professor Dr. Engineer Werner Enderle, who is the head of the Navigation Support Office at ESA's European Space Operations Center in Darmstadt, Germany. Previously, he worked at the GSA as the head of systems evolutions, in charge of evolution activities for Galileo and EGNOS. He also worked for the European Commission as responsible for activity related to Galileo geodetic and time reference, definition of the Galileo high accuracy service, and also for the procurement of the Galileo ground control segment. Before these assignments, he was a professor for aerospace at the Queensland University of Technology and the director for navigation at the Australian Cooperative Research Centre for Satellite Systems. Dr. Enderle started his professional career at DLR, German Space Operations Center, in the Space Flight Dynamics department, where he was leading a variety of activity related to orbit and attitude determination based on GNSS. He was also the initiator for the development of a GPS receiver for sounding rockets and small satellites at DLR. In this context, he was also coordinating a cooperation between DLR and INPE in the area of space flight dynamics. Werner Enderle holds a doctoral degree in aerospace engineering from the Technical University of Berlin. So, Werner, the floor is yours. Thank you.
So, first of all, thank you very much for this kind introduction. And in this context, what you just mentioned, I had some interactions with INPE. And Roberto Lopez was especially the point I was working quite for a while together. Some of you may probably know him. So the idea is here really to provide you an overview of Galileo precise orbit determination, what we're doing at ESOC, but also, let's say, scope not only focused on Galileo, but for all GNSS satellites. Now, very quickly, I will hopefully, let's say, make it short with respect what the ESA Navigation Support Office is doing. Then I will come back to some basics. Probably you have already heard about that related to the satellite orbit determination. And then ESOC's approach for this, how we're doing it, Galileo precise orbits and clocks determination. And then we're looking into the results. So what is the Navigation Support Office are doing? In ESA, or within the European Space Agency, all of the respective organizations, divisions, or offices, they are in charge for a particular part of, let's say, area which is needed for providing access to space. And the Navigation Support Office is entrusted with all activities providing or related to precise orbits and clocks. That is with a main focus on GNSS satellites. Here the focus is on Galileo, but also we're providing the orbits and primarily the precise orbits for user spacecraft in different orbital regimes, like LEO, geotransfer orbits, HEO, and now in the future we will provide also this service for Earth-Moon transfer orbits. We're also providing the geodetic reference frame for all ESA missions. In addition to that, we're also contributing to the UTC. That means we're generating something which is called ESOC UTC or UTC ESOC. And this is the time reference for all of the operational stations which are operated and globally distributed for the ESA missions. In that context, we're operating a global real-time network, which we call AGON. You will see that on a later stage. This is a network of real-time sensor stations where we're tracking all of the GNSS constellations which are up there. We are also analysis center for different international activities that you have in principle for geodetic measurements or observation techniques which are related to the precise orbit determination. One of them is GNSS, so therefore we are an analysis center for IGS. Then for the satellite laser ranging, the international organization is IRS. The DORIS, which is an onboard precise orbit determination device, this is IDS. And then also with very long baseline interferometry. And here we are at the moment associate analysis center because we started this to join as analysis center only 2 years ago. And I think that we are one of the few centers around the world which are involved in all of these, let's say, activities as an analysis center. Looking right now what we're doing related to Galileo, precise orbit determination, we have been involved since more than 20 years in precise orbit determination. And now you say, well, Galileo was not existing at that time. That's correct. But Giove was basically the precursor for the Galileo, and we did quite a couple of activities with this as well. One of the activities was the modeling, that means generation of the orbit dynamical models, especially of concern. You will see that or hear that a couple of times today, at least in this let's say presentation. Of key essence is the solar radiation pressure. This is SRP deprivation, then albedo, attitude models, and all related dynamic, let's say, models which are really driving the accuracy of the precise orbit determination capability of GNSS satellites, in particular for the Galileo. Then we were involved in clock modeling and clock characterization. We have validated, let's say, all the metadata. Metadata is data which is publicly available, which was released from the European Commission to the public so that they can, for instance, have information about the PCV is the phase center variation, PCO is the phase center offset. So this is antenna related. Then we have box wing parameters. This is basically the shape of the satellite. That means for the Giove, but also for the Galileo satellites. We have been involved in investigations in different type of performance investigations and anomalies. Also, when the satellites were going in the wrong orbits, then the sensor station analysis and performance. And we also involved in research activities, doing different type of studies related to Earth orientation parameters, ambiguity resolution, and let's say additional activities supporting science. Be providing operational orbits to the ILRS, that means the International Laser Ranging Services, so that the stations around the world, the laser stations, can track the Galileo. And then we are also the coordinator of a European consortium, which is called GGSP, and we providing the operational Galileo geodetic reference frame. Now, coming to the basics, and I apologize if you probably have something like this already seen, so therefore, but I think it's important in the overall context to understand our approach. So what we have is essentially the situation that we're saying the basic concept is you have, and here I hope you will see my mouse. This is a reference trajectory, which we believe the satellite is flying, but because we don't know the truth. And so therefore, what we essentially using is we have a kind of options to model. That means the reference orbit. And then what we can do is we can also have measurements. And based on these set of measurements, we can have right now the requirement that we are doing on-board or real-time, then we're doing basically non-real-time and on-board, or we're doing non-real-time on ground. And the concept I will really highlight is the following, because this is what we're using. This is an orbit, then, or let's say a dynamic orbit determination concept. That means the dynamic orbit determination means we're modeling all the forces that are acting on the satellite. Based on this, let's say, equation of motions, we numerically integrate, oops, sorry, this was the wrong way. We numerically integrate them, and therefore we reconstruct the measurements. And then we combining the measurements or the reconstructed measurements with the real measurements, and then applying a suitable concept. In our case, this is a least square method, where we try to, let's say, making sure that we combining the knowledge of the orbit based on the dynamics and combining them with the measurements, and we processing them in order to get the most accurate part, or let's say the most accurate estimates of these orbit parameters in a post-processing. That means we process it on ground and using data arc. Data arc would mean from here to here. But the essential task is to determine the position and velocity and also additional parameters. This can be quite a few of them at a specific epoch. Namely, in that case, we're using all the measurements to calculate the position or the state vector, which is, let's say, including position and velocity at a specific epoch, which would be then here. In addition to that, we have to make sure that we are using an appropriate, therefore I have indicated it here, a reference frame. And in that case, we're using a terrestrial or inertial reference frame. Normally for this orbit, for this dynamic orbit determination, we're using at ESOC a inertial reference frame, which is then basically with the epoch of J2000 and then transferring it to the epoch which of interest for us. Besides this, let's say, concept, you have two other basic principle concepts. That is a kinematic orbit determination. The differences to the dynamic is that you don't have to basically include any orbit modeling of the forces. You only use the measurement themselves for the orbit determination. Again, no modeling for the forces is requested here. And for instance, the position, velocity, and time, which you probably have heard since the last couple of days, this is a typical, let's say, kinematic, let's say, approach. This kinematic orbit determination can be done for real-time or post facto, and using also a single epoch or multiple epochs. Different concepts or sub-concepts are applicable to that. Then you have a reduced dynamic orbit determination, which is a combination of the dynamic and also the kinematic. And normally you're using that in the context also of a Kalman filter. But the basic principle is that you should, based on measurements in the dynamic orbit determination concept and the generation of the reference orbit, you should combine that and be doing it with the least square. Now, you can do that if you're mapping, because we're talking about right now, let's say, the orbit determination of the GNSS. You have the possibility to simply use a network. So we have a network on the Earth, and this is, therefore, you see this really as a net. That means you can connect all the stations to each other. Now, if you have the GNSS satellite, and here this is just the indication that you have basically not only one constellation, but multiple constellations. So you can use the data which you receive on the ground stations or the network on the ground stations for the orbit determination of this different type of GNSS satellite constellations. In that context, there are also multiple variations what you can apply. For instance, you can do a single, that means you're using the data for one single satellite, or you can use the data, therefore I made a network here, that you really have a network approach, so that you're processing, for instance, the GNSS satellites, which you have indicated here, it's GPS and Galileo, that these constellations will be processed in one single process together with the estimation, not only of the orbits and clocks, but also with the station coordinates and additional parameters. So that you have basically, as I said, a network processing approach. And this has some mathematical benefits, but it's more difficult to process. And you see later on some of the figures that this means to process quite a bit of data. But this is one of the concepts. Now, on top of that, you can have also a further, let's say, improvement. That means that if you, for instance, have additional satellites available in space and you have access to the data, you can process them together as if the satellites let's say in just for example in the low Earth orbit, as if you would use them as nothing else as a station which is not on the ground but in space. So this is additional complexity, but it has some benefits. So at ESOC we have all of these three options. We can do a single orbit determination, that means using the network for a single satellite, or we processing all the things in the network together. And on top of that, we can also use the data of the GNSS receivers on board of LEO satellites. So this is the most complex part. Going to the next one, just to let you know what is the situation in terms of the network. This is, for instance, one of the networks which I just mentioned. This network, which we essentially have right now, established. At the moment, we have 25 operational stations and with different, let's say, capabilities. Some of the stations we also releasing the data to the IGS. Some of the stations we are using in Europe for UREF. Some has external reference clocks. And so you see here the different capabilities. And here, these are the deep space stations, for instance, here in Argentina, in Malague, or one of the stations you see here, one of the 24 operation stations. I think this is a quite, let's say, a familiar spot. And this, let's say, has been implemented, this station in Brazil in 2019. And it's operational since then. So important for that, why I'm showing that is because the network has a quite significant impact in on the precise orbit determination. And what is important for precise orbit determination is essentially that you understand the geometry, and this means that the ground station distribution over the globe is really an important aspect. I give you an example. For instance, if you're going here in Hawaii, this is a station, there is not a lot of land there. But to have a geometry which is, let's say, equally distributed over the entire globe, this is essential that you have the capability to have stations also on some remote places. Sorry, going back to that. So that one element is the geometry, how you measure. And the second one is the quality of the measurement itself. And here we have for the entire station, all of this entire, let's say, ground network, which we call EGON, is actually executed. That means all of the data is coming into ESOC in Germany, and which is located here. And from there, we then redistribute the data. But we have all of that, the real-time streams, they're coming into ESOC, and we then process it. And we have for all of the stations one and the same type of receivers and also calibrated antenna. So important for precise orbit determination, it is key that you have a good geometry and excellent measurements. So that means, as an example, if this station is not working or not operational, then we have a problem because you see there is nothing in the vicinity here. And that means that the observability of the orbits has an issue, which should be avoided. Good, going to the next one. What we did, but this is right now not only for Galileo, because as I said, we're doing also something which is called multi-GNSS. And for the multi-GNSS, we're not only using our own network, we're using network from IGS, because we are a funding member of IGS. And so we're also using the data from 150 stations. And this is optimized. That means we're not using all of the stations from IGS. We're only using stations which allow to have a good geometry. So equally distributed, that would be very good. Now, if you're looking further, what I said before, namely, the impact if we're using on top of our ground stations also LEO satellites. And here I simply give an example how important that could be. For instance, in 2018, we had 19 stations deployed. So these are the 19 stations we deployed. Now, what we did, we said, okay, if we right now combining that with satellite, because there are satellites from Sentinel, these are elements of the Copernicus program, and we had access to these data. So we simply said processing all together. And what you see here on the, let's say on the right-hand side, is basically the geometry and the coverage. So you not only have the coverage, which is basically from the ground stations, you have also a coverage which is coming from the respective satellites. And if they have a rotation, which they're doing, they're flying around the Earth, so that means you're getting quite a good coverage on the globe. Now, if you're not using only one, if you here on the bottom left, you see that we're using more sentinels and let's say 4, let's say visible satellites of the, let's say the GNSS, then you see that we have excellent geometrical coverage. And even if you're using 6 satellites, that means all of the sentinels, this is then a fantastic situation because this is improving the geometry significantly. Again, the complexity is significant, but it also improves actually the overall situation. And again, it is beneficial if you have not so many ground stations, but in order to improve then the geometry, you can use this concept of adding satellites from the respective LEO. And in some of the, let's say, global navigation satellite systems, they are considering exactly this concept and augmenting their, in the future, the systems with a LEO, let's say, constellation part. Now, going further, because, and here coming back to the Galileo precise and orbits part, we have different concepts, and this is depending what we really need. Here we have, I simply provide you with an overview. We have different software suites. One software suite, this is our workhorse in essence, this is called Napeos. This is a batch processing system, and it has a high precision orbiting clock determination and prediction capability. And we estimating, as I already said, all, and here I called relevant parameters and products in a single run. So that means that, or in a single process run. So that means that we have the station coordinates, the Earth orientation parameters, the some parameters for sure, the state vector, that means position velocity, then parameters with respect to the satellite clocks, and in addition, the clocks also of the ground stations. So, and then we have some parameters for our, let's say, models, which are modeling, for instance, solar radiation and also albedo. So all of that can be done in a single, let's say, process, but it is, as I said, quite complex because of the number of, let's say, equations and also the stability, numerical stability of the big, I would say, nonlinear equations, or the number of nonlinear equations. So we're using this with, as I said, as a normal, but we have something which we're doing at the moment. This is, I think, not experimental status is not correct anymore. I should have updated that. It's a pre-operational. We already using that. And this is, we're calling it EPODs. This is an ESOC precise orbit determination system. And this is a similar thing, but the huge difference is that, and I'm coming to this a little bit later, we processing in this new software suite all observations. And that means whatever a GNSS, let's say, system provides on signal, we processing it undifferenced, and we using no linear information. We're calling this method as a raw method, and this has a huge benefit It is more complex to process, but it is more realistic in terms of physical, let's say, realization of the real processing of the data. I will come back to this part in a couple of minutes. And then we have the capability in this new software to processing all of the 4 observation techniques, geodetic techniques, namely GNSS, SLR, DORIS, and let's say VLBI. ISL is inter-satellite links. This we had on top, but all of the geodetic part, in addition, inter-satellite links, which is also, let's say, under discussion for future satellite systems. We have the high precision orbiting clock determination and predictions. This is important, the prediction part. That means this is actually driving basically a lot of effort, namely how good you can model the things. And the estimation of the process, this is, as I said, sometimes quite a complex part because not only of the number, but also some of the, let's say, needed partial derivatives, which you need for the orbit determination or the estimation process, is quite complex to get. So then we have another suite, and this is right now something which is, let's say, going away from the pure batch processing. We also have the need to do real-time GNSS processing. Therefore, we have a software suite, which means Retina. And this is basically a combination. It uses input from our estimation, from our prediction. That means we're predicting orbits within Napeos and then giving or handing it this over to the real time. And we have here a real-time filter for the clocks estimation. And here we have then the capability that we do a real-time processing based on a precise point positioning algorithm. And so this is used, for instance, for monitoring all of our stations in real time, but also to do in the future, we're working at the moment on that. We're doing it for the spacecrafts so that we are able to do a PPP for the satellites. That means user satellites in LEO, HEO, or GTO. Now, if you're looking to the process itself, so the dynamic POD concept, as I already said, we're using at ESOC a batch processing part. And here I don't go into the status where we are because the results are showing that it's quite good. But the important part is area for improvements. And here what is really important is the solar radiation pressure. And you will see how there is an evolution done, what is necessary for that in the next slides. But important is that the clock models, because the clock characterization and let's say modeling of the clock, it's art by itself. And if you could, for instance, let's say replace the fact that you don't have to estimate the clocks, but you could basically, let's say, use a clock model instead of the estimation of the clocks, that would be then a completely different approach and would makes the things much more stable because the clock behavior is high frequent. And this is completely contradicting the behavior of the orbits, which are very smooth. And if you have to do a estimation process with 2 completely different behaviors, this is from a numerical point of view, not so trivial. Now, the Galileo orbit prediction part, as I said, here we have several issues to consider. Even if you have our models that is to a certain extent, let's say, increased to a very good level of accuracy, but there is something which is really critical, especially for Galileo compared to other satellite systems. Namely, if you're looking that the mass surface area, or let's say a surface area which is related to the solar radiation or exposed to the solar radiation pressure force, this is in Galileo relatively small. And other satellites, which are much heavier, for instance, a GPS satellite, they are not so much affected then by this force. So in Galileo, we have a couple of challenges where others this don't have, simply by the construction or by design. And if you're looking at the Galileo orbits and clocks estimation process, this is the third element of the entire concept. As I already stated before, the number of the stations, but is the pure number of the stations. It's not the let's say the most useful criteria, because just imagine you have all the stations in Australia, then you would have hundreds of stations, but the result for the orbit determination would not be good, because it's depending on the observability. And therefore, the geometry of the station and also the quality of the observations, this is the key. And we have at the moment the Galileo orbits, actually we saying at the same level. In fact, we are with Galileo better with respect to the estimation as with GPS. And this is despite the fact that the, let's say, the network solution we have from Galileo, because it's smaller. There are much more, let's say, stations around the world. They can track all except the new GPS signals. But the old GPS signals on the L1 and L2, they are tracked by nearly every stations, whereas not all of the, let's say, stations can track all the Galileo signals. So this has an impact. And also you have to think about the number of satellites, which are from the individual constellations. That means the more satellites you have in a network solution, the more stable the solution is. And also this has an impact on the accuracy. But you will see that as well. So this is this equation. I simply would like to highlight only 2 or 3 elements. We don't go over everything, and I believe you see different types of this style. But what I would like to highlight is the following. Actually, here I have to first start. This is actually an error. It should be not R. It should be T. Just get rid of this R here. But there is an important element here I would like to highlight. Namely, you have different elements in this equation. This is for a code measurements. And you see here that it's depending on the frequency indexes, but it's also depending on the individual signals. So that means the frequencies, and you have on the different frequencies, as you have learned or heard, you have different type of signal on the same frequency. Now, the important part is you have different time scales. And one is actually the time scale of the GNSS. Let us assume it's Galileo. That means you have the Galileo system time. And this is when the signal will be on, let's say, emitted from the GNSS satellites or the Galileo satellite. Now, the reception is done normally in also a specific receiver time. And that means, for instance, if the receiver, just imagine that it's just a Galileo only receiver, then it's fine. Then it most likely will also measure the signals in a, let's say, time scale, which is the same as the transmitter. But if we going away that we only have one constellation, then suddenly you have different time scales, because the time scale of GPS and Galileo are different. And that means that you have to consider that there is a time difference for that. And on top of that, it is also as such that even if the receive time, or you measure or you look what is on your watch at the time when the receiver receives the signal transmitted from the satellites, but then it could be that you are not, let's say, processing it at that time. That means there must be a third time scale, which is actually the processing time scale. And why I'm mentioning that to this extent, because it's important to understand these things, and all of these corrections are here. So a term, this is a code phase measurement, and this is right now basically a geometrical part. Sorry. Yeah, the first part is the geometrical distance between the satellite transmitting point and receiving point of the antennas. Then you have corrections with respect to the travel time. You have corrections of the geometry. and you have then different corrections with respect to the different timescales. And then you have, for instance, where is the slant tag? That means this is the ionospheric part. And then you have uncalibrated code delays from the different, let's say, signals in the different frequencies on the satellite side and also on the receiver side. And then you have additional code, let's say, corrections. There's maybe multipass or other observation noise, which is not considered by the terms. But again, depending on the application, this looks different. So you have to adapt that. And certain consequences are, if you're using this, for instance, the same equation for a LEO satellite, then certain elements, for instance, the troposphere, this needs to be taken definitely not into account. The ionosphere, depending on the altitude which you're flying in, has to be taken into account or not. Or if you're going to, let's say, a high eccentric orbit, then you have to partially of the time, if the perigee is within the, let's say, area of, let's say, 1,000 kilometers, you have to consider the ionosphere. And if you're going to the apogee, most likely not. So this is a generic, but we're using that, and then we have a different type of corrections which we can apply. Now we're coming to the next part here. And this is the orbit determination parameters. So what you see here is starting from the left-hand side in the top, this is the state vector and the a priori covariance matrix. And this is for the parameters. So you see on the left-hand side, this is the state vector containing the position, velocity, and then you have addition, namely certain, this is the alpha 1 to alpha k. These are certain other parameters, can be ground station coordinate or other things. Yeah. Then you have an observation vector and a priori covariance matrix for the observations. So that means if you're only using code, then you have here what is typically the error or the 1 sigma value for the code, or you have it for the carrier phase, which is much smaller. Then you have an observation residual vector. That means the residual vector is essentially what you observed minus the calculated. That means the reconstructed. And then the key idea is to have, for us, what we're using at ESOC is that we have the method of the least square. That means the errors which you have here, or the residual vector, should be minimized. So that means you're generating a loss function, which is a function of the, let's say, error square. And then we are requesting that this should be minimized. And this leads then to normal equations. And you see here the normal equation set. And then based on the fact that the equations are nonlinear, the observations and the equations of motion, and therefore we have essentially to linearize that. And therefore what we're doing, we have something which we call normal equations, and they have to be solved then in an iterative process where they iterate as long as we have certain criteria, thresholds fulfilled, and essentially we don't see any change anymore. Complex topics is the design matrix. This is these F. This design matrix is basically the, let's say, the observations partially derived with respect to the parameters we are looking for. And sometimes it's very difficult to have these partial derivatives, and all of them you can have analytically. Some of them has to be done also numerically, or very hard to get anyway. Then the residual matrix is basically then the differences basically between the observation and the calculated. So, and all of that will be put together. Then that means we at ESOC using a for this process a dual frequency, ionospheric free. If you're using two frequencies, then you can generate a linear combination so that the ionosphere will disappear. This is the boundary conditions. And then you can generate that for the code and also for the carrier phase observations. And normally we get with this approach quite good, let's say, results. The POD is based on multi-frequency, again, minimum 2. in the future, we already using for our experimental, or let's say pre-operational part, actually not only 2, we're using all frequencies what we can get, and we are using them, as we said, in an undifferenced and with no linear combinations. That means also we can directly estimate, for instance, the ionosphere, and with physically meaningful values. And this is improving actually the POD accuracy. And this will be for us, this raw method, for the future, this will be the standard. And the more signals we're having, that means not only, let's say 2, the more signals we're using and the more frequencies, the better this raw method becomes. A key of that all is ambiguity fixing. Ambiguity fixing has to be applied for carrier phase measurements, not for code measurements. That means that the fixing of the ambiguity is the outmost, let's say, accuracy you can achieve, but it's a mathematical, or it can be a quite challenging process. And but it is for the orbit accuracy at the moment the limit you can achieve. And so therefore, to give you a little bit of a flavor right now, and also how complex this could be. What we did is the following. You see here a slide which shows, for instance, this was from 2016. And we have here a box wing model. That means simply we have a XYZ in like a cube, and then we're using that in order to modeling the effect if the solar radiation pressure is more or less acting on this cube. Now, if we're seeing that how we calibrating that is actually via the satellite laser ranging. On Galileo, we have on certain, let's say, satellites, a laser reflector. And what we're doing is we try to calibrate then our dynamic modeling with the real measurements. And here you see we have basically on the right-hand side, we have, oops, sorry for that. We have here a what we're getting out as on the two-way ranging to the satellite from the ground station, and as a function of an argument. And you will see later on, if you go into the next one, we improve that because we switched here. We have no box wing model applied. Here we're having a simple box wing model applied right now. And what you see here is that on the right-hand side, it's getting much, much smoother. Now, if you go into the next one, and if you're using a box wing model, which is improved with the characteristics, that means not that we are improving the cube, but with the surface characteristics, that means the material and also aging of the material has been much better modeled. And then you see that the entire, let's say, this modeling effect, which we had deficits in 2018, we have improved significantly. So we're using SLR, satellite laser ranging, as an independent source for, let's say, I would say monitoring, or at least validating our orbital dynamic models. And now we're coming to the future. We're going away from the box wing model, and we actually applied already in our latest software the ray tracing. So that means we call this ARPA, aerodynamics and radiation pressure analysis. So that means we're making very complex ray tracing, and this will be used for non-gravitational forces. But we need to know very precisely the geometry and surface properties. And this allows us to have a very good modeling of the radiation pressure and air track. So the air track is especially for LEO. This is not affecting the GNSS satellites, but the SLR is significantly impacting. Yeah. So we're going to the next one, which is the ambiguity fixing. If you're looking at the ambiguity fixing, it's basically the following. There is a natural integer number, which is simply the distance between your sending antenna and receiving antenna. And because the wavelength of the individual frequency has a certain amount, if you would know and you measure the distance between let's say the sending antenna point and the receiving antenna point, you would have a number dedicated and a number which is an integer number of cycles, and then you have something which is a fractional part of an entire cycle. And now what we're making, we're using linear combinations at the moment for our method based on the ionospheric free combination. And we're using double differences between the network and also between the satellites. So between the satellite itself and also with respect to the network. And then we're looking what kind of accuracy we can achieve. And what you see on the right-hand side, you see before fixing, that means if you're getting a solution which is simply not made as such that the numbers you are estimating for the differences are integers. And you see that this is a quite different, this histogram shows that basically if you have it not fixed, the cycle ambiguities, then you see the fractional parts have a much different, let's say 1 sigma value, as you're using the one in the light blue. This is when they have been fixed. So in the ideal case, you would have only one of these arrows, or bars, and that would be in the middle. That would be then perfect. So we have a fixing rate higher in the meantime. This was, I think, some time ago. We have it right now higher, I think higher than 99%. And the number of different double difference observation we're using here is, as you can see, basically, or which have been really used for the fixing. This is varying, but it's quite a bit. And if it's a, let's say a network, it's definitely also further increasing, depending on the number of stations. It's clear. This is something what we calculating as well, namely the so-called differential code bias. This is the this is needed. These are the code bias between the different signals, and so these are needed in order, as you have seen from our let's say observation equations, in order to have the utmost or getting a good accuracy level. And this is also then important for the level of accuracy we can achieve. And they are estimated over daily, not each epoch, or daily. And what we can see, it's quite stable over quite a number of months. Now, what I would like to show you on this, let's say, slide is actually what I said before. Namely, if you're looking at 2014, we had just a, let's say, a relative small number of satellites up there. And this was basically the number of satellites which you see there. And the scale is on the light blue on the right-hand side. And now we definitely have more satellites. And the point which we are simply would like to make is what you see is the overlap at this is a kind of the overlap at the day boundaries, because accuracy is relative. Accuracy is not something which is absolute. How you measure it, or you need to have a certain parameter or criteria where you say, okay, this is basically a consistency check. And that means what we're doing is we simply looking at the day boundaries. What is the consistency over time? And here you see over several years, over 8 years, and how we have improved the, let's say, level of accuracy essentially for the processing of the respective GNSS or Galileo satellites. So this is depending on the number of really the satellite itself, the quality, and also the operational stability. Good. If you're going further, this gives you a little bit more in values. So for the Galileo system, we have the IOV. This is called the in-orbit validation phase, or the FOC, it's final operational. This is also not quite correct because Galileo is not in the final. So it's basically, they're still the final operational part, but these are the FOC satellites. And what you see here is the day boundary overlaps. Let's say the 3D values for FOC is about 38 millimeters. And the important part is if you're looking at the, let's say, the satellite laser ranging, which we're using as a kind of independent cross-check, you see that the values what we're getting there is also quite consistent. So that means that we're using satellite laser ranging in order to also independently evaluate what we're getting out on our orbit determination based on GNSS only. And here we have also comparison between the Galileos and the GPS. And here you see as well that we, despite the fact that we have more satellites from GPS as Galileo, that we're getting quite good, let's say, and consistent numbers. Therefore, I was saying previously in the same order of magnitude. Galileo is slightly better. Now, that means that what we're doing here at ESOC is actually not only processing Galileo. This is a prime focus in order to support the project and Europe Commission. But we're processing all the GNSS. And that means that the interoperability and the number of pure, let's say, signals is a key to that. So today we're processing, let's say, 123 satellites. That means in orbit are nearly 140, but the operational is only 123 in all different orbital regimes. Yeah. And if you see here, it's not only the 4 global, we also processing QZS, which is a regional system. Now, what we're doing because of the time, this is also something which is important. GNSS is something which is always relative to something you need to have references. So, and the reference time is a very important one. So in the ESOC multi-GNSS, let's say, processing, we're using actually not only the ESOC Maser station, we're using something which we call a ensemble clock. In the old, and this is what you see on the left-hand side, we used one reference clock. And the reference clock was selected out of the network. Now we're using 10 of the clocks, which we have monitored over several years, and we know that they have a very good performance. And then we're using this ensemble clock. This is a pure paper clock, and this is then our time reference. This makes us much more stable. It's not the accuracy, what you see here. With a single reference, we came to 70 picoseconds, but if you're using ensemble, this is not only the accuracy, but the stability is much, much better. Now, if you're looking what we're processing right now, if you're processing all, the routine analysis, to give you a flavor of, let's say, what I said before, we have around 30 million observables per day. This is coming from the 100, let's say, plus GNSS satellites. We have to do the ambiguity fixing. Yeah, we're doing this on a one-day arc, and we're getting to a level which is around, let's say, a little bit. At the moment, we are around 2 centimeters. And the constellation we are processing is GPS, GLONASS, Galileo, Baidu, and QZSZ. We actually providing you with this data. That means it can be downloaded. And you see the data products, and you see also our website here. And if someone has an interest, they can go to our website and look at our products. And the quality of the products, again, we're looking at the day boundaries. From the left-hand side, which is Baidu, you see the quality of the overlaps. This is a relatively new, this is in 2022. What you can read essentially is the following. That GPS and Galileo, this is the light blue and the orange, they are on the same level of orbit, let's say, consistency at the day boundaries, whereas the others, that means the Baidu and also the GLONASS, they have very strong variations within the constellations, but they are in general not as good as Galileo or GPS. Now, as I said, the final products you can download from the site, and here is just an overview. I don't want to spend too much time. This is just, this is what we make publicly available in order to support really also development around the world. And what is, let's say, given here at the end, and I don't want to go into the details here, it's just a, let's say, an overview which should give you a flavor of the complexity, which is, let's say, behind all the software and all the results we're having here. That means Earth orientation parameters. You see here what we did. The terrestrial reference frame, this is a key. We also, because we are in IGS, we contributing to the terrestrial reference frame, and actually we did the reprocessing so that there is a consistency between the 2014 terrestrial reference frame and the new one, which is the 2020, which will be released very soon. So in all of these, let's say, different type of effects, we have to actually take into account. Here you have even a second list, which is important. It's simply to give you an overview that what kind of elements you have to, let's say, think about. And please have one thing in mind with the observations. We have right now gone away from the 30 seconds. We have right now second sampling. So that means a factor of 30 with respect to the observations we have to process, and the observation type, which is at the moment, let's say for the nominal ionospheric free linear combination, but in the future, we take every single observation we simply can get. And this is again increasing the number of, let's say, things or observations we have to process significantly. So a challenge is actually how such big, or let's say such big, let's say data processing. This is a challenge by itself, I can tell you. And with that, actually, I'm coming to the end. And I think we are 2 minutes ahead of the schedule. And I definitely would like to thank you very much for your attention. And I think now I'm open for any questions you may have.
Thanks, Werner, for this very nice overview on all of. Can you hear me?
Sorry, I can't hear you. There is a huge echo. Hello? Okay. I can't hear anything.
Hi?
Yeah, now I can hear you. Yeah.
Okay, sorry. Yeah, I think the mic was muted. Thanks very much, Werner, for this very complete overview of all of the activities that are being performed at ESOP. It is really impressive, all of the work you're doing in both post-process, real-time, different approach. I am checking the Google Meet chat, and we do not have any new question. And now I will open the floor for questions in the room. Is there any question here, or you are all of you are looking for the lunch?
I would say lunch.
There are no questions, and thank you very much. It was very clear, and thanks again for participating as an external speaker in this Galileo masterclass. Thanks, and have a good afternoon, Werner.
Not a problem. I have one final request. Would it be possible that you send me also these the link to the recording? That would be appreciated. Yeah.
Sure. We will publish on the website GIG all of the PDFs together with the recordings, so it will be accessible for everyone. This we will be doing after we finish the event. In the meantime, I can send you the Google Drive and make sure that you can access. Okay.
Yeah, not a problem. And well, bon appetit, and enjoy your lunch. Yeah. Okay.
Thank you. Have a good afternoon.
Thank you.
Bye.
Yeah. Bye.